Hello, everyone. Here, Giacomo Beccari speaking again. Thank you very much for being with us today with the new event of the Hypatia Colloquium. Actually, I apologize because up to now I've been pronouncing Hypatia. The way Hypatia is the way in Latin, I understand in Latin, we pronounce T-I-A. So Hypatia is the way, or Hypatia is the way you pronounce it in a beautiful language, which is a Greek language. So I hope I get it properly spelled. But anyway, welcome back to the new event of this series of talks dedicated to early career astronomers. Let me just very briefly remind you that the participant, we have a group of participants on the Zoom inside the Zoom meeting. So those will be able to make questions directly themselves once the chair will give you the floor, and the other channel is the YouTube channel where you can post your question, and this will be then passed to the speaker by the chair. Please be sorry. Consider that there is always a 20-second delay, more or less, between basically the event on YouTube and the event which is happening live on Zoom. So consider 20 seconds. So this can cause sometimes some asynchronization between the time you basically the event is going on and the time you make the question. Anyway, all the questions, is nice that you post your question on the chat on YouTube, because basically this way the speaker will have the chance, if the question is not answered on the spot, is that they have the chance to see the question and then send an answer later. Also consider that you can always contact the speakers. If you go to the pages of the Hypatia pages at www.eso.org, that you see ESO HG, you see basically a web page with the program, and on the program for each of the speaker you can click on the title of the talk, and you can download the CV of the speaker, and so you can find also the contact details. So if you want to get in touch with the speakers, and also the link to these videos and to all the past videos are also there, so you can go there and have a look at the talks. It's a very, very beautiful data set. We are really proud and very enjoy it a lot, this series. I want to also to mention as a last point that there is another, so we saw that there are a few other events happening around us, still with the same very scope that we are doing here. So they are dedicated to early career astronomer. If we have linked, for example, an event that is happening on our colleagues in Australia, the Australia Seminar Series dedicated to early career scientists. So we had added, so we decided to basically collect all these initiatives on our pages, on the Hypatia pages. So please, if you are an organizer of such event, or you get to know that such events are happening, just send an email to us at esohc@eso.org, and we will be happy actually to try to collect all of these in our database, in our pages. Having said that, I think I can now give the floor to our chairs. Today we have Michele Ginolfi and Ronald. That they are a fellow and a student at ESO, to absolutely enjoyable and bright student and fellow of us. We are very happy that they're helping us and they are chairing the session. And now I would like to give basically the floor to Michele, who should be opening the actual talk.
Yes.
Michele, there, very good. Welcome. Thank you to you, and thank you to Roland also for being with us, and see you later.
So good afternoon to everyone. I'm Michele Ginolfi. I'm ESO fellow in Gotking, Munich, and it's a great honor for me to be chairing along with Roland this Hypatia session. And so our first speaker is Kathryn Grasha, which did her PhD in Massachusetts, USA, working with Daniela Galzetti, and she's now a postdoctoral fellow at the Research School of Astronomy and Astrophysics in Australia. and she will be talking about the Stromlo stellar track and the importance of non-solar scaled abundances for massive stars. So Katie, the floor is yours. If you want to start sharing the screen, please go ahead.
Right. All right. Can you hear me and everyone can see my screen?
We don't see your screen.
No, you don't see my screen?
No.
Oh.
Michele, yes.
Can you try again? Okay.
Yep.
All right. Yes, we can now.
All right. How's that?
It's good. Go ahead, please. Thanks.
All right. Thank you everyone for coming, and I also want to thank the organizers, for giving me the opportunity to talk at this series. So my name is Kathryn Grasha, and I said I'm a Astro 3 fellow at the Australian National University, where it's currently 1 a.m. in the morning. So be nice to me. No. And so today I'm going to be talking about basically the very first implementation of non-solar scale abundances for stellar tracks using the galactic coordinate scaling system. Oh, there we go. So this is, really important because, stellar models are basically the backbone to interpreting observations. And its observations of stellar populations are a really major component in understanding the physics of the galaxies. And this is a complex problem, and it isn't just the stellar population that's limited by our stellar models. It's the nebular modeling as well, because sometimes we forget that the area surrounding a nebular area is part of the star cluster too. And so it's feedback from these high massive stars that shapes the ISM, and it impacts the gas that will form future generations of stars. So it's our understanding of how these stars form, how they live and ionize their surrounding medium, how they evolve, and die and deposit these newly enriched metals into their ISM, then how those become the next generations of stars is a really important part to understanding the physical conditions of star formation. And models really play a key role in our understanding of the interaction between star formation and a galaxy environment. And as it currently stands, I will argue that stellar tracks prohibit basically our physical interpretation of observables. And that's because, this is a really complex problem because full rate of transfer cluster and nebula modeling requires numerous inputs and assumptions. And most crucially, an accurate estimation of the central star cluster spectrum is really critical for the production of realistic nebular models. And so this requires detailed stellar atmosphere and stellar evolution tracks. We convolve these through a stellar population synthesis program such as FSPS or Starburst 99 to build up a realistic composite spectrum. And then we can run these through photoionization models such as cloudy or mappings. And then we produce, our expected nebular emission, which give us our outputs that we all, care and love about, metallicity, star formation rates, ionization. But a really crucial limiting factor that plagues models and outputs is the stellar tracks. And there is a concern in standards and consistencies between what's currently available. And these differences essentially they cast doubt on the reliability of combining track and atmosphere data into population synthesis applications. And so I'm going to talk a lot and focus on metallicity because, this is something that I really care about. And so metallicities, this is a key property understanding galaxy evolution. And it's because your gas phase metallicity, oopsie, nope, not yet, sorry. It's your gas phase metallicity that sets the balance between the processes that enrich gas, such as star formation, and processes that dilute or remove metals, such as, inflows of pristine gas from the intergalactic medium, galactic winds, and outflows. And the relationship between metallicity and other fundamental properties place really tight constraints on governing the evolution of galaxy. And it's the correlation between our global metallicity and stellar mass in galaxies, what we call the mass-metallicity relationship, is one of these fundamental relationships for measuring the chemical evolution of galaxies. And I'll just say that, the redshift evolution of the mass metallicity is very uncertain. And this is because, testing model predictions and systemic effects from insufficient resolution from stellar models basically inhibit our ability to reliably measure metallicity and metallicity gradients at high redshift. And so the models are not sufficient to reduce the systemic scatter that we quite often see to interpret high redshift observations. And so I'm going to go now right into the challenges of stellar tracks and 3 challenges that I've identified, and then how we're hoping to do this. And this is really important because observations of our SCPs depend very critically on our stellar track inputs. So here we're showing starburst 99 clusters, luminosity as a function of energy, wavelength on the top, and your ionizing photon output rate, very highly depends on your metallicity. And this is what gets us really into trouble is we have a very coarse grids of metallicity for stellar tracks. For all of you who are familiar with, say, starburst 99, we can only run available models for like 5 metallicity grids, and they're all scaled to solar. And this really isn't good because if we want to calibrate or we want to fit spectra, then we have to interpolate between the available coarse metallicity points. That's because that's where the stellar tracks are available. So if we want to measure true metallicities, 5 metallicities simply will not be accurate. We're going to need stellar tracks at a much finer grid because metallicity matters. The second point is that stellar tracks are all from solar or solar scaled, alpha enhanced, things like that. And so to derive relative abundances at non-solar abundances, uniform scalings are always used, but different solar abundances sets have different scaling factors. And this matters because elements don't necessarily scale well with metallicity. So on the left, we're showing here like neon to oxygen blue or argon to oxygen in the green. And you can see that once we reach for like our neon above a gas phase of 8.5, neon doesn't scale with gas phase metallicity at all. Or on the right, we have different scales of metallicity of, say, chlorine to oxygen for different solar sets, or just they have different standards. And this is important because relative abundances in solar, you simply can't scale them to produce the relative abundances of what we see in H2 regions within the Milky Way, LMC, and SMC. And this assumption of non-uniform scaling is really important in nebular modeling. So in our left-hand model, I'm showing oxygen 3 to H beta emission line ratios as a function of N2 to O2. And you can see in the gray, we're showing Sloan data. And in the black grid, we're showing uniform scaling, solar uniform, where we scale it up and down consistently. Where we're scaling it up and down uniformly. And we see it does not really match the data. But when we scale it non-uniformly, we see that our red grid matches the data much better. And on the right, we're seeing what happens for different standard scales. And we're seeing that even if you change your relative solar, as long as we're always uniformly scaling to solar, we can't really match our data. And so we need to approach this problem starting with the models. And the assumption is, that all models exist are solar scaled, but the universe simply is not solar, especially for O stars that dominate the ionizing budget. And so what we need is stellar tracks, atmosphere, and nebular modeling. If we go back to the outflow chart that I showed earlier, we all need these to be self-consistent and have the same inputs on the same scale. And with this, then we can start to answer questions such as, how do abundances behave on low metallicity? Because we don't have a handle on this, and this prevents us from addressing known issues, and such as our mass metallicity relationship and its evolution over cosmic time. So what we use is, instead of solar, we use the galactic concordance abundance set. And so this is abundances scales that are derived from fits to modern stellar and H2 regions over the full range of metallicity. And you can see we have these for all elements. I should say the first 30 elements. And you can see here as for oxygen, magnesium, and silicon, of where we go and we take nearby stars, usually B stars, and we go and we measure their relative contribution to iron, and then we fit functions as a function of metallicity, of our Fe over H. And this is what we call the galactic concordance abundance set. And so this is basically just matching the abundances, and it's a scaling set for what we see in local H2 region, and it forms the backbones of our stellar tracks. If you want to know more about the galactic concordance and these non-solar abundances, I will refer you to the Nichols et al. 2017 paper, which outlines the scaling parameters that we use. So once we have our abundances at different metallicities, we create new stellar opacity tables that use the same abundances. You know, opacities are really important because your energy transport in your star and the mean free path will depend on the relative ratio of the metals. We run our stars in MESA using the MIST framework, and I'll get into both these in the next slide. So we import these tables and galactic concordance abundances into MESA. Well, I'm really focusing on very hot and high mass stars, so things between 10 to 300 solar masses. We use different types of solid body rotation, 0, 0.2, and 0.4. So 0 is non-rotating, 0.4 is rotating at 40%, you know, the velocity needed to break up your star. And I use metallicity grids from -2 to 1/2 in steps of 0.1 dex, so very fine grids. But if you remember, in the galactic concordance scaling system, because every metallicity has a different functional form with, every element has a different functional form that's fit with metallicity. So we cannot uniformly scale metallicity. And so every time we change our metallicity step, we have to go back and recalculate a relative fraction of abundances at that metallicity, and then re-import those opacities, recalculate those opacities, import those into MESA. So MESA is the modules for experiments in stellar astrophysics, and this is a 1D stellar evolution package. And MESA is really well suited for this purpose because it has this flexible architecture and is capable of self-consistently evolving stars from, you know, different types of stars from, you know, pre-main sequence to advanced stellar evolutionary phases in a single continuous calculation. And the thing that's really nice about MESA is because it has these thread-safe modules to enable parallel computing, and this is true for both the numerics, which is, you know, your matrix algebra and your interpolation, as well as your input physics, such as your opacities and mass loss. And so each of which are an independent functioning unit that generates, tests, and exports a library to the general MESA library directory. And one of the advantages of this is, you know, you can go and you can tweak a physics or implement new physics, and that's fairly straightforward, and then that doesn't impact other modules as well. So I use MESA within the context of like MIST, which is the MESA isochrones and stellar tracks, and MIST presents models with solar scale abundances covering a wide range of ages, masses, phases, and metallicities computed at solar within a single framework in MESA. So MIST basically helps us with the input choice at a given runtime of this endless file, which contains, you know, the user choice of parameters for the input physics, time steps, mesh steps, and output options. So we adopt the physics prescriptions and parameters of MIST, which is outlined in Troy, and then Roy20 also outlines the changes we made to the MIST framework for our massive stellar models with galactic concordance abundances. All right, so we've created a whole suite of tracks from 10 to 300 solar masses for galactic concordance. That's what the GC means, and solar for reference. And so for those who are listening who aren't super familiar with looking at HR diagrams, luminosity versus temperature for massive stars like 200 solar masses, I'm going to step through this a little bit. You know, going from A to B, you know, this is our pre-main sequence, where B, you know, your hydrogen starts fusing in the core. Evolution from B to C is your main sequence when the star lives. C to D is your Haney hook. So this is where our star starts to contract in order for helium to fuse and to ignite at the surface of this newly made helium core. The evolution from D to C is our subgiant branch. So we have 8 shell burning. And then the evolution from D to, my computer was lagging. The evolution from E to F is, and so when we have our RGB tip, we get our helium flash, so we start to have helium core burn, and then we evolve from E to F. From F to G is our helium shell burn, and then we become an asymptotic giant branch, and I always evolve my star until the end of carbon burning. So for high mass stars, these evolutionary phases don't really have the same significance, such as the RGB tip, because stars are able to, say, bypass, the thermally pulsating AGB branch and proceed to later phases of core burning. But oftentimes you see, when we talk about stellar, massive stellar tracks, we keep these evolutionary phases for consistency. But now what I want to do is, we're not going to really look at these tracks too much, but we're going to go and zoom in and try to look at how assumptions in the models, are, we're going to take solar, we'll compare it with what we got for galactic concordance, and we'll look at the resulting things like SEDs. But before we get to that, we're going to look at the impact of abundances and rotation on our tracks. So here you can see we have some HR diagrams where pink is showing our Stromlo tracks with galactic concordance abundances. The blue to yellow are showing the same, but for solar, so using Asplin 2009. And so on the left panel, we're showing metallicities of 0. And you can see, by definition, at solar metallicity, the tracks are about the same. But as we move to slower metallicities, we see that, there starts to get some deviation in solar versus galactic concordance abundances. And then on the bottom here, what I'm showing you is the impact from just rotation. So we're only showing I'm only showing the Stromlo tracks, and the solid line is showing rapidly rotating stars, and the dotted line is showing non-rotating stars. And here again, you can see that the impact becomes more important at lower metallicities. So the impact of rotation on stars in determining, your effective temperature, gravity, luminosity, which is all related to your mass loss and surface abundances, this is new, this has been known. But we see that abundances play a very similar role in determining these stellar parameters as rotation, where the impact matters more at low metallicities. And so the differences really start to add up at the extreme end. So if we take, some very massive stars, say here 300 solar masses, and the orange is showing what it would look like in mist, and the purple showing what it looks like from Stromlo, you can imagine that if you throw this 300 stellar mass star into, a population synthesis program, the emission lines and the H2 region properties that we get are going to look very different. And then before we start looking at SEDs, I have one more plot of where we are showing the surface helium mass fractions as a function of time for solar -1 and -2 metallicities. The dotted line styles are showing different types of rotations. So solid line is very rapidly rotating, dotted line isn't rotating at all. And then in the purple, this is a 200 solar mass star, a 100 solar mass star in pink, and in the very light pink is a 60, low mass star of 60 solar masses. So here we can see that rotation in stars above about 100 solar masses heavily impacts the surface composition. So as a result, massive rotating stars will actually spend the vast majority of their lives on the main sequence with enhanced helium surface abundances that are consistent with the Wolf-Rayet stellar evolution phase. And basically non-rotating stars, there's no diffusion mechanisms for the transport of chemical elements from the inner convective core to the outer shell. So therefore, we don't see the same type of surface enhancement. And the effect of rotation mixing enhancement of the surface composition increases with decreasing metallicity. All right, so these tracks are all fine and good, but we really want to know is, how does this impact our observables? So we see there is probably an impact, and the impact matters at lower metallicities. But how does this actually impact what we see? What type of synthetic spectra do we get from these tracks? So I've used FSPS, which is the Flexible Stellar Population Synthesis Stellar Population Program, to easily generate spectra, and you can do it for magnitudes as well for arbitrary stellar populations. FSPS is very modular, so it basically allows you to just insert your own stellar tracks to model the stellar population. And I will say that the plots I'm showing you, I'm using the default model spectral library within FSPS because we're using Tosca or CMFGen as an atmosphere code to self-consistently match our galactic concordance tracks, and that's not yet set up. So we're not yet being self-consistent like I would like. And so it's really important when we're looking at these synthetic SCDs. So on the left, we show for mist at solar metallicity. On the right is for galactic concordance abundances or Stromlo tracks. The only thing we're changing is the elemental abundances. And there are many key nebular lines and energies that are greater, between to singly ionized hydrogen, doubly ionized helium, singly ionized helium and doubly ionized helium. That's what these vertical bars represent. So this indicates that, small changes in the stellar tracks between singly and doubly ionized helium will potentially have a large impact on our nebular ionization and subsequent nebular lines that are important for local metallicity and star formation rate studies. And so what we're showing here is basically I've added up. So we're showing Q, which is the time evolution for the ionizing photon rate as a function of age. Pink again is Stromlo, blue is using mist, and these are for energies to singly ionized hydrogen, singly ionized helium, and then the dotted line doubly ionized helium. So you can see, again, solar metallicity, it's all about the same, and the differences really start to add up. And the differences really start to add up when we move to low metallicities. And we can see that here when we get to metallicities of -2 for energies that will doubly ionize helium, the differences at a given age, especially at very young ages, can be off by a factor of 2 DECs. And so, solar is over predicting by a significant amount at these low metallicities. And this will have a really important impact on our emission line ratios. So now I'm at my summary. I'm not sure how long I've been talking, but I think I'm about up. So up until now, all stellar evolution tracks are computed at solar scaled or alpha element enhanced abundances. And this does not represent what's observed in local H2 regions. And so the Stromlo stellar tracks are the first implementation of galactic concordance abundances to stellar evolution models. And this is really important because galaxy concordance abundance scaling provides a more realistic approach than simple uniform abundance scaling with metallicity for the analysis of H2 regions. And it has a considerable impact on interpreting observations because our relative ratio of elemental abundances greatly impacts our ionizing spectra. And this has really broad implications for measuring line ratios and star formation rates and metallicity diagnostics. And so I'm going to argue that this is really important for high redshift observations, especially with the oncoming James Webb or the next generations of, our extremely large telescopes, because in order to understand and properly interpret these high redshift observations, it requires that we start with calibrated, self-consistent, and a comprehensive picture of how stars are ionizing the local star formation sites at low redshift and how that depends on factors such as geometry, metallicity, and abundances in order to understand this process at high redshift where we lack observations. And so it all starts at the foundation of refining our existing stellar evolutionary models as a first step for comprehensive high redshift extragalactic studies. And I will end there.
Well, thanks a lot, Katie. It was very interesting and clear. So let's see if there is any question in the Zoom. Well, yes, we have, I can see one hand raised. So Hil-Sang, do you want to ask a question?
Yes, thank you. Thanks. Hi, Katie. This is very nice talk. Thank you very much. This might not be very much related with what you are working on now, but I'm very curious if this non-solar abundance calibrated on the galactic, concordance models, how does that impact in the cooling function of the ISM in general? Do you have any comments? Will that significantly impact the cooling function? So we expect different, the ISM physics for star formation in general?
This is a really good question that I have actually never thought about until now, like how this will impact the cooling function of the ISM. And I think it will probably be important. And so I don't have a good answer for you right now, but this is something that I think is worth thinking about.
Very good. Okay, we have also a question by Giacomo, actually. Please go ahead, Giacomo.
Can you hear me? Yes.
Yes.
Thank you very much, Kathy. Really a lot of interesting plots, and so I've been a bit looking into models at the very beginning of my career, but now I'm not really. But I was just curious about some comments I wanted to ask you about. Some, for example, in one slide you mentioned that it is easy to generate magnitudes for general stellar populations.
Oh.
But
okay, maybe I shouldn't have said easy.
Yeah, exactly, because because it is. Yeah, exactly. Can you comment on that? Because
because
it is. Yeah.
Oh, sorry. Did you finish?
No, sorry.
Yes. Okay. So I personally, in my work, don't calculate magnitudes or do any conversion of the SCDs into magnitudes because it's actually not super straightforward.
Yeah. Indeed, it is not. And on the other side, also the opacities. I wanted to ask you the stellar opacities. This is one of the most critical ingredient, right, as an input to the stellar models. But so I didn't understand. You said on slide 13. You say we create new stellar opacities.
Mm-hmm.
Right. I didn't. But can you? Because I didn't catch exactly that.
Okay. Yeah. So we use the opal opacity methods.
Okay.
So it's based, so you can go and you can just generate, you can input your relative ratio of, so the thing that basically limits us is, opacities get really complicated when you have to include molecules.
Yeah.
Okay. And so, but luckily we don't have to deal with this because we're dealing with, very hot stars, things over 10 solar masses. So, usually greater than 40,000 degrees Kelvin. Opal then generates this for these types of opacities at these hot temperatures relatively easily. So you can just go online. It has a really nice web interface, and you can just enter in your relative abundance for some elements. I can't remember off the top of my head. I think it's the first 15 or so, and it actually and it goes and it spits out your nice abundance tables, which are and then MESA is actually will go and read in that format as is.
Mm-hmm. Okay, nice. Thank you very much.
Thanks, Katie. And okay, I think we have time for another question. So please, Dietrich, go ahead.
Yeah, a very impressive piece of work. But you anchor all your abundances to local H2 regions.
Yes.
And Rolf Kodritsky has for decades been arguing that one should not use H2 regions and the abundances of H2 regions, but the abundances determined from stellar atmosphere analyses. So what is your position on that?
So this is an excellent question, a very good point that you raised, and we are actually trying to go back and do this. So to go, and especially for O stars in the LMC and SMC, and measure their stellar spectral features to constrain those elemental abundances to redo this work. Okay. Because so this is something that we're actively trying to do now, to go and improve on. Does this make you feel any better?
Okay, there is also, all right, okay, we have a couple of minutes more. So I think can ask the questions which was put on the YouTube, which is, do you also use new set of equation of state table for the new abundant set?
No, we do not. We use the same equation of states, all that kind of stuff as outlined in MIST, which was made for solar abundances.
Okay. Okay, just for reference, the question was asked by Xiaoting Fu. Okay, I think we are approaching the end of this first part. So thanks again, Katie, for the nice, interesting talk. And now I will ask Roland to go on with the second part of the session. Please, Roland, go ahead. Thanks.
Yes, thank you very much, Mikhail. So after this amazing talk by Katie, we come to our second fantastic early career astronomer of today, called Jorryt Matthee. He did his PhD in astronomy at the Leiden University in 2018 and is now a Zwicky Fellow at ETH in Zurich. And today he would like to talk about the resolving reionization with high redshift analogues at cosmic noon. So please go ahead and share your screen, and the floor is yours.
Thanks, Roland. Let's go. Audio and video is okay? Yeah, okay, thanks. So, yes, thanks for giving me the opportunity to be here to give this talk. Actually, some of the aspects of the previous talks are relevant for the interpretation of observations that I'll present in this talk. So that's a nice bridge. This is work looking at distant galaxies at cosmic noon, which is redshift about 2, which means we're looking back at galaxies as they were roughly 11 gigayears ago. But this is work done in collaboration with all my fantastic collaborators listed here. So the question behind this work and the main motivation is to trace early star formation through cosmic time. I'm personally mostly interested in finding and studying galaxies that are in the very first phases of their formation. And by definition, those galaxies are powered by very young, metal-poor stars, the first generations of stars in these galaxies. One local example is this galaxy Zwicky 18 in the very local universe with an extremely low metallicity. In my opinion, the best way to trace early star formation is using emission lines. In particular, emission lines from ionized recombination lines from hydrogen, because they are not sensitive to abundances. Hydrogen is very abundant, so these lines are typically also quite luminous. And two particular lines that I want to highlight are the Balmer alpha or H alpha transition, which I'm sure many of you are familiar with. It's in the rest frame optical, which is nice for observing it in the low redshift universe. It's also not very susceptible to attenuation, at least in not extremely dusty environments. We don't expect young galaxies to be extremely dusty. But the big downside about H alpha is that it's not observable currently in the first 3 gigayears of cosmic time, and that's because it redshifts out of the K band. It redshifts into the mid-infrared, where we need the James Webb Space Telescope to observe this spectroscopically. Another line that is connected to H alpha is the Lyman alpha transition. It's a different transition, and intrinsically it's actually 8 to 9 times more luminous than H alpha. This line is in the rest frame UV, which in principle is great for high redshift studies because it redshifts in the optical in the early universe for galaxies that we observe in the early universe. Using this feature, many galaxies have been found historically with narrowband surveys on, for example, the Subaru telescope. More recently, the VLT, in particular the sensitive IFU MUSE, has been very successful in identifying extremely faint Lyman alpha emission, either extended emission or compact emission from very faint galaxies. But there's one big issue with Lyman alpha, which is that because it's in the UV, it's sensitive to dust attenuation much more than H alpha. But in addition to that, it's a resonant transition, meaning that Lyman alpha photons are scattering if there's neutral hydrogen present. And I'll address this in a bit more detail because it's quite crucial for the background of my observations. A very simple picture of a distant galaxy. If we observe it from Earth, let's assume it's a single H2 region with some stars in it, and let's assume there are some gas clouds in between. So UV continuum photons, non-ionizing photons, they can travel freely between these clouds because I did not include dust in this picture. Lyman alpha photons, however, if they travel from those stars towards us, some of them actually may be lucky and they don't encounter any neutral hydrogen. The fraction of these galaxies are, these photons are probably very low because galaxies tend to have neutral hydrogen in their ISM. However, if Lyman alpha photons travel through the ISM, what typically happens is that it scatters when it encounters neutral hydrogen in a random direction, and it also obtains a velocity shift. And this scattering to first order, what it implies is that the path length that Lyman alpha photons travel between the H2 regions and us, or when they're traveling through the ISM of galaxies, the path length is much longer than it is for UV continuum photons. And for example, if you imagine that there's dust in some of these clouds, UV continuum photons not necessarily see those clouds because it just depends on the direction. Lyman alpha photons are much more likely to see those dust grains just because they scatter. Because of this, the Lyman alpha luminosity can be reduced significantly, and the actual fraction of Lyman alpha photons that we observe is not very well known. And this is a big issue in interpreting Lyman alpha observations, for example, in terms of the star formation rate, and also in terms of what types of galaxies do we actually see. Scattering also impacts the Lyman alpha line profile. If we would just observe it directly from an H2 region, it would likely trace the motions of that region. We almost never observe that. If Lyman alpha photons scatter through neutral hydrogen, then scattering leads to redistribution in frequency. So you get this double peaked feature. And depending on the actual velocity of these clouds, the Ryan ratios of these peaks can vary, and also the distance between these peaks. And to first order, the line ratio depends on the velocity, and the separation of the lines depends on the amount of neutral hydrogen. So using detailed observations of the Lyman alpha transition can actually help us studying the properties of the ISM, in particular the neutral ISM. But again, as I said, this remains poorly understood. One reason for that is that all those galaxies that we observe in the distant universe, let's say above redshift 3.5, where Lyman alpha is observed in the optical, we typically see a spectrum that's only this white part on the left part of this diagram. It's basically this Lyman alpha line and some UV continuum. Often we don't even see the continuum because of sensitivity constraints. On the other hand, if you look at the low redshift universe, we have all these very useful emission lines that we can use to learn about the gas phase metallicity, the star formation rate, the dust attenuation, and many more properties. But we cannot observe Lyman alpha for these galaxies because we need a UV instrument. It has been done for a few galaxies, of course, with costs on HST, but it's very challenging to do for larger samples. So to fix this issue and to try to empirically study the relation between the Lyman alpha line and well understood red frame optical emission lines, we have been undertaking a survey at redshift 2, which happens to be cosmic noon. And this is the redshift where you can observe Lyman alpha from the ground because it's redshifted just beyond the UV atmospheric cutoff. And H alpha is still not redshifted enough. It's still in the K band, so it's not high. It's not redshifted into the infrared background. In particular, we actually targeted Lyman alpha emitters, so with a similar selection method as the very distant galaxies, with narrowband imaging. From this target sample, we then selected 20 in our own survey and combined those with 15 galaxies from the archive, leading to a sample of 35 Lyman alpha emitters, galaxies purely selected through Lyman alpha emission. And we followed those galaxies up with the X-Shooter instrument on the VLT. X-Shooter is a single object shell spectrograph, and its main strength for this study is its very long wavelength coverage. It basically covers all emission lines that are relevant for our study. And the resolution for Lyman alpha is actually quite good, the spectral resolution. And it's a factor 2 to 10 better than typical surveys at high redshift. So our objects were observed for typically 2.5 hours per source. And we tried to sample a dynamic range in relative equivalent widths of Lyman alpha. So we could do some studies on how this equivalent width depends on some properties. And finally, I have to note that we removed a priori AGN using X-ray and radio data. So the survey was quite a success. We confirmed almost all galaxies that we targeted. Note that none of these galaxies was known before and none of them had a spectroscopic redshift, but they were pre-selected with imaging data. The Lyman alpha lines are shown here. Don't study them in detail, but what you can grasp from this is that they mostly show, as the illustration that I showed earlier, there is a double peaked profile, and the redder peak, which is always redshifted from the systemic redshift measured from red frame optical lines, is always stronger than the blue line. For two objects, we did not see an oxygen tree line. So I want to first show what the typical properties of these galaxies are, and we did that using a stack. Of course, it's great to have individual galaxies, but you can get much better signal to noise when you stack data, and then you can learn something on the average, on the median Lyman alpha emitter in your sample. And that tells us something about what are galaxies that we select through strong Lyman alpha emission. So the stack looks like this. We see all these strong emission lines, Lyman alpha by selection. There's also O3 and H beta in the H band, and then H alpha here. In the UV, there's lots of interesting features that some of them I'll point out later. You can see that for the stellar mass is actually quite low. The mass is 10 to the 9, which is roughly a tenth of the mass of the Milky Way. And this means that we are looking at galaxies 10 gigayears ago that had the mass that the Milky Way had at that time as well, roughly. The star formation rate is slightly higher than we believe the star formation rate of the Milky Way was. The dust attenuation is actually, it's on the low side, but it's not extremely low. What is interesting about these numbers is that this mass, there's no reason for the mass to be low. And we observed a very large volume. So in principle, we could have picked up massive galaxies if they are Lyman alpha emitters, in particular because massive galaxies have higher star formation rates. So the fact that our Lyman alpha emitters have a relatively low mass implies already that high mass galaxies are typically not Lyman alpha emitters, at least at this redshift. So what can we learn from the spectrum? The first thing you do is plot the galaxies on the BPT diagram. This is not obvious at high redshift because you typically cannot observe H alpha. We see that these galaxies, the blue point is relevant here. We see that the Lyman alpha emitters are on the star forming part of the BPT diagram, meaning the photoionization is done by stars and there's no hidden AGN that we missed. The oxygen 3 to H beta ratio is relatively high. And this is similar to other studies at high redshift, targeting slightly more massive systems mostly. And it means that the ionization state of the gas is slightly higher at high redshift than it is in local galaxies on average, seen from this BPT diagram. From the emission line ratios and the equivalent widths of the lines, we can infer that the actual stars that are powering these galaxies are young. They're only 20 megayears on average and are metal poor. We see helium-2 line emission, nebular helium-2 line emission, as Katie showed, or actually discussed in the previous talk. This is ionized by very hard photons with energies above 4 Rydbergs. The stellar atmospheres, the effective temperatures of the stellar atmospheres need to be at least 50,000 Kelvin. So you can imagine that the strength of these lines depends a lot on your stellar models, what Katie just showed. If we use recent models, BPAS models in particular, we can interpret these emission line strengths with a metallicity that's quite low. It's less than 10% solar. It's slightly lower than the gas phase metallicity. We measured gas phase metallicity. It's expected to be low for this high redshift and this mass. What is more interesting than only metallicity is that we also measured the carbon to oxygen abundance in the gas. And what this shows is that the C2O abundance is actually quite low. It's much lower than it is in the sun. And that is basically because the carbon yields lag the oxygen yields because the enrichment is from different types of stars, and there's also the fact that the carbon yields depend on metallicity. And what a low C2O abundance tells you is that we are basically observing gas that's predominantly enriched by core collapse supernovae from a single early starburst. So this is consistent with this picture that Lyman alpha emitters are really are going through their first burst of star formation. What we also see from the Lyman alpha emitters is that the ISM, even though the mass is quite low, the ISM contains several evidence for having outflows. We see outflows in 3 different ways. We see first this Lyman alpha profile that is skewed towards red. I'll discuss this profile in detail slightly later. We see broad wings in oxygen 3 in a few individual objects and also in the stack. These broad wings could indicate high velocity gas that's relatively highly ionized and is believed to be a tracer of outflow activity. More directly, we also see that interstellar absorption features like silicon-2 are blue shifted with respect to the systemic redshift. So this also indicates that the silicon-2 absorbing gas is outflowing, moving towards us. Perhaps these outflows actually help these galaxies to be observable in Lyman alpha, because if we combine our average properties of Lyman alpha emitters with other surveys and compare the galaxies that we selected with other samples, we can basically conclude that there are 3 different processes that determine whether galaxies are Lyman alpha emitters. And these 3 are the relative production of Lyman alpha photons, which really is basically the hardness of your spectrum. Basically, how many ionizing photons do you produce per UV continuum luminosity unit? This traces the age and the metallicity of stars. Basically, if you have younger ages and lower metallicities, your galaxy is more likely to be a Lyman alpha emitter. This is not the only story, because you also need to have a relatively low dust attenuation. But in addition, what may be even more important is that in the ISM, you need to have channels illustrated here with these white lanes, but note that they are not necessarily lanes, because Lyman alpha photons can scatter through even a lane that has some corners. But the amount of neutral hydrogen in the ISM determines how often Lyman alpha photons scatter, and that also determines whether they can escape easily. And we believe that all these 3 different processes depend on stellar mass. And that explains why low mass galaxies tend to be more likely to be Lyman alpha emitters than high mass galaxies. Even though at redshift 2, based on our number densities and based on the clustering and other studies, Lyman alpha emitters are still rare among the low mass galaxies. Among galaxies with a stellar mass of 10 to the 9, only about 10% is a Lyman alpha emitter. But we know that this number needs to increase towards high redshift because the cosmic Lyman alpha escape fraction, which is basically the integral of the Lyman alpha luminosity density from galaxies divided by the star formation rate density. And this increases from redshift 2 to 6, as you can see here. At redshift 2, the cosmic Lyman alpha fraction is only about 3% or 4%. While at redshift 6, which is just at the end of the epoch of reionization, the number is about 30%. What this implies is that galaxies that are Lyman alpha emitters are more common at high redshift. And the galaxies that we study at redshift 2 actually have this typical Lyman alpha escape fraction that galaxies at the epoch of reionization have. And what this means is that the processes in the ISM that determine the radius transfer of Lyman alpha in these galaxies are comparable to average galaxies in the epoch of reionization, which means that we can use them as middle redshift analogues. Of course, to explain this, regardless of reionization, to explain this evolution, either of these 3 different effects that impact the escape of whether galaxies are Lyman alpha emitters could be important. It could be that in the early universe, galaxies are less dusty, the stars could be even hotter, or the ISM structure could be different. And all those processes could contribute to the observed evolution of the global average. And in order to use, so I think using Lyman alpha and in the future red frame optical emission line studies with James Webb, we can address which of these explanations is more important. And we can learn a lot about the properties of young and low mass galaxies as they evolve through cosmic time. Finally, in the last few minutes, I want to talk about reionization because this was in the title of my talk. Lyman alpha has been, because it's sensitive to the amount of neutral hydrogen in the ISM, it's also sensitive to the amount of neutral hydrogen in the IGM. And therefore, Lyman alpha has been used to learn something about the neutral fraction of the intergalactic medium. And it's basically that if you go to a more neutral universe, Lyman alpha tends to be absorbed or tends to be scattered into possibly the infrared background because of this neutral hydrogen that is present. Based on this property, we can use Lyman alpha to infer what the neutral fraction is. And we can also, more detailed, we can see specific galaxies where from the Lyman alpha profile, in particular where it cuts off very sharply in the blue, we can actually determine the size of ionized regions around galaxies, because this cutoff is really set by the damping wing of the intergalactic medium. So Lyman alpha observations like these can be used really to learn about the topology of reionization. In addition, Lyman alpha observations are also useful to learn how reionization happens. And that is because this Lyman alpha profile traces the escape fraction of ionizing photons, and how the escape fraction of ionizing photons depends on galaxy properties, influences how reionization happens. That's illustrated in this picture. In purple, this is the evolution of the neutral fraction with cosmic time. In purple, bright galaxies dominated the reionization budget. In that case, reionization happened quickly and late. If low mass galaxies, faint galaxies dominate the ionizing budget, reionization happened much more gradually and slowly. And the Lyman alpha profile will be different for different kinds of scenarios. So the key question really is what is this profile and what can we learn from this? I'll just show the average profile, redshift 2. And the average profile at redshift 2 is has this double peaked signature. And we can learn two things from that. One is from the peak separation, we can learn what the typical H1 column density is that the photons have seen. So basically the grayscale in this cartoon picture of galaxies. In addition, the valley flux, that's what we call the amount of Lyman alpha photons that can escape directly at systemic redshift, so without scattering. They trace how many of these scattering-free chimneys in the ISM exist. And both these properties, the column density of the ISM and the amount of very low column density channels, basically column densities below 10 to the 17, they both scale with the escape fraction of ionizing photons. And using empirical calibrations of the escape fraction of ionizing photons, we can infer the escape fraction of ionizing photons for these galaxies from the Lyman alpha line. So we use these empirical relations from very low redshift analogues, and those imply that the escape fraction in these galaxies is about 5 to 10%. And this is exactly, on average, the value of the escape fraction that you need for galaxies to dominate the reionization budget. Of course, the question is not, did galaxies reionize the universe? Because we know reionization happened, and we are quite convinced it's star formation in galaxies that dominated the budget because other sources are just too rare. The key question is how the escape fraction varies with galaxy properties. Were it massive galaxies or low mass galaxies? And just to end, that's what we're exploring in the future by studying, instead of the average Lyman alpha profile, which is shown here on the left again, we can also study the variation among these profiles, because in individual galaxies, because they tell us much more on the mass dependence and any other dependence between the ISM structure that determines the escape of ionizing and Lyman alpha photons, and any other properties. We see some exciting objects, and stay tuned for the future to learn about those results. I'm just going to leave my summary here, and I hope you enjoyed, and I'm happy to answer any questions, either now, or you can always contact me through email or on Twitter. Thanks.
Thank you very much, Jorryt, for this great talk. So are there any questions so far? Let's see. There is one question by Mikkel. Go ahead, please.
Yes, Jorryt. Thanks a lot. So my question is actually more a curiosity. Did you plan to follow up any of these galaxies with ALMA, maybe trying to get any constraint on the dust mass at some point? Is it? I mean, I guess it's tough, isn't it? But maybe for the monster-forming galaxies in the sample could be feasible.
Exactly, yes. Initially, I was not planning to do this because I just had to I had the idea that it would be impossible for these low mass systems, but a few galaxies are slightly more massive, so it's definitely worth I think to try to map the dust. It's also interesting to see this with high resolution because there is red stream UV imaging from HST, and if you can get ALMA dust map with ALMA at similar resolution, it's interesting to see where the dust is compared to the UV and the emission lines. But in principle,
did we just lose the connection?
I think he's back again. Jorryt, I think we missed you for a couple of seconds.
Okay. I'm getting a warning that my connection isn't stable. I'm not sure if you got my reply to ALMA.
Yes, I think we missed only the few final words.
Not very relevant.
Okay, thanks.
Okay, any more questions? I don't see any on YouTube right now. Giacomo, I think raise his hand first. Go ahead, please.
Yeah, mine was just a very, very technical question, actually, Jorryt. As a successful shooter user, so this is very technical. I wanted to ask you, how is it? Because I saw the spectra that you showed, they are beautiful telluric feature removed, and so exactly. I mean, as I said, it's very technical, but I wanted to ask, how was it? How did you achieve that?
Well, so actually, the main wavelength regions where the telluric are important are masked. And by select, so redshift 2 is really a lucky redshift because all the important emission lines O2, O3, and H alpha are not affected very strongly by telluric. There are skylines, which are a pain. But one property that really helps for O3 is that it is a doublet with a fixed ratio. And then, I mean, it's very rare that both the O3 lines are affected by a skyline at the same rest frame velocity. So
yes, indeed.
So that helps basically, like looking. I imagine it as looking like on the edge of the skyline. But yeah, the big telluric regions are luckily not very important for us.
Yeah, so thanks. Sorry.
Okay, then we have another question by Dietrich. Please go ahead.
Yeah, very nice and very clear presentation. Thank you very much for that. Have you tried to compare your results to simulations such as Illustris?
We did not do that, and the main reason the question is what to compare, I think. It would be very nice if simulations like Illustris would provide Lyman alpha luminosities or even Lyman alpha line profiles, because it can tell something about the ISM. But the radiative, what I've learned from simulators is that the radiative transfer is very expensive to do, particularly because you need a high resolution. The resolution of Illustris it's not ideal to do radius transfer of Lyman alpha, I think. I mean, we could compare, of course, other properties like the mass, but I think it's more interesting to compare to do comparisons with radiative transfer simulations. I am aware that some are being done.
Yeah, I understand this. I was thinking of the clumpiness in particular.
Yes, this would be. I think it would be interesting to check, but I'm not fully sure how the simulations deal with the clumpiness, in particular because they have a cooling floor. I mean, the simulations don't cool indefinitely because then they don't have the resolution for that, and they put all the ISM particles on a predefined relation. So I'm not fully sure. If someone knows it, then I would be quite interested. I mean, it's also, we didn't quantify clumpiness from the Lyman alpha profile. The profile on itself just qualitatively implies clumpiness, but there's no quantification that's easy to compare. That's a great, but I mean, it's an obvious thing to do. Yeah, thanks.
Okay, I think we're out of time and out of questions too. So thank you very much for the talk, and I'll leave it to Giacomo for some last closing words, maybe.
Yes, indeed. Thank you very much. First of all, I would like to thank again Roland and Michele for chairing the session. Thank you thank you very much, and thank you to Jorryt and Kathy exactly for the great talks. And you have a lot of applause on your YouTube channel, just to let you know, so you can see the applause in end. And in particular, maybe Katie, she basically thank you very much for being with us, Kathryn, at this time, because I know it's 1 a.m. in the morning for you, so it was really appreciated. And I mean, now you can go, hopefully take your time to rest. But thank you very much, and say hello to our colleagues in Australia, actually. And so as I said, so the talks will stay online, so you can go and watch them on YouTube later. And also, please remember that the details of the speaker of both Kathryn and Jorryt, they are available online. So if you go to our pages, you go to the program page, then you can click on the title, and then you can download the CV. And so you can get in touch with our speakers again in the next future. So with that, we can close the session again. Thank you, everyone. Thank you also for the people who attended, and see you next time. See you in a week. Thank you very much again. Bye-bye. See you.